What if I told you there's a book that's basically the instruction manual for the universe? I'm talking about Isaac Newton's Philosophia Naturalis Principia Mathematica. Yeah, it's a mouthful, so let's just call it the Principia. This one book didn't just tweak our understanding of science, it completely rewired how we see everything.
So this was published way back in 1687, and it laid out the mathematical rules for time, space, and motion. Now, it's famously dense, like notoriously difficult to read, but the core ideas, they're actually incredibly elegant. So today, let's unpack them and see how Newton literally built a new universe from the ground up.
Okay, so to really get why this book was such a bombshell, you've got to picture the world before it. Back then, it was like the universe had two different sets of rules. You had one for us down here on Earth, and then a totally separate, kind of mysterious one for everything up there in the heavens. I mean, just think about this for a second. An apple falls straight down, right? But the moon, which is also getting pulled by the Earth, it falls around it. Why the difference? That was the big question, the giant puzzle that hinted there was a deeper system at play that nobody had figured out yet.
So, to tackle this massive puzzle, Newton knew he couldn't just jump straight into equations. Nope, he had to go back to the very beginning. He had to define his terms, create a shared language so that everyone was on the same page.
First on the list, mass, or in Newton's own words, the quantity of matter. It's pretty much what you think it is, how much stuff is packed into an object. But, and this is where it gets really clever, he proved that an object's mass was directly tied to its inertia. How hard it is to get it moving. That link was a total game changer.
All right, next up is space. And for Newton, space was, well, it was absolute. Just picture this giant, unmoving, three-dimensional grid that stretches out forever in all directions. It's the stage where everything in the universe happens. It doesn't change, it doesn't move, it just is.
And you know what? He thought of time the exact same way. Absolute. Imagine a universal clock, somewhere out there, just ticking away, tick-tock, at the exact same speed for everybody, everywhere, no matter what. The steady, relentless flow of time was the rhythm for everything that was about to follow.
So with these definitions locked in, absolute space, absolute time, and mass, Newton had set the stage. He was ready to reveal his masterpiece, the laws of motion. And these weren't just some clever observations, these were the fundamental rules of the game for the entire universe. Let's start with law number 1. It asks a pretty simple question. What happens when you just leave something alone? No pushing, no pulling. This is all about what he called inertia. And the answer is so simple, but it's profound. An object that's not moving is going to stay not moving. And an object that is moving is going to keep moving in a straight line at the same speed forever unless some outside force messes with it. That's inertia. It's that feeling of being pushed back into your seat when a car floors it. Your body wants to stay put. Okay, so that's what happens when there are no forces. But what about when there are? Well, that brings us to law number 2. And this is where things get really interesting. This one is probably the most famous equation in all of science. You've definitely seen it before. F equals ma. Force equals mass times acceleration. It's so elegant, right? The more force you use, the more something accelerates. But, and here's the other side of the coin, the more massive it is, the more force you need just to get it going. This one little equation is the engine that drives all of classical physics.
And what's really cool is how Newton showed that you can actually add forces together. Think about it like this. You've got two people pulling a boat. One's pulling it north, the other's pulling it east. Where does the boat go? Not straight north, not straight east. It goes northeast, kind of diagonally. Newton showed you could map this out with perfect geometry, which made a messy world suddenly seem very predictable.
All right, on to the third and final law. And this one gets at something really deep about what a force even is. Turns out there's no such thing as a one-way push or pull. It's always a two-way street.
Here it is. For every action, there is an equal and opposite reaction. It means forces always come in pairs, always. You push on a wall, and guess what? The wall is pushing back on you with the exact same strength. You literally can't touch something without it touching you back.
And this isn't just about walls. This is universal. The Earth pulls on the moon, sure, but the moon is pulling right back on the Earth. That's what gives us our tides. It's a cosmic dance. A rocket shoots hot gas down, and that action pushes the rocket up. It's the same beautiful principle at work everywhere. Okay, so we've got these 3 beautiful, simple laws. But so what?
They're just rules on a page, right? Well, this is where Newton pulls it all together. This is the grand finale. He took these laws and used them to build his system of the world.
And here is the big aha moment, the mind-blowing reveal. That force that makes an apple drop from a tree, it's the exact same force that holds the moon in its orbit. The moon is literally always falling towards us. It's just moving so fast sideways that it keeps missing. Suddenly, it's clear. There aren't two sets of rules for the universe. There's just one.
So when he put his laws of motion together with this new idea of universal gravity, boom, everything just clicked. He could perfectly predict the weird elliptical orbits of the planets. He could tell you where comets were going to be centuries from now. He could explain the tides. The universe wasn't some big mystery anymore. It was a system you could understand.
You know, what's just as revolutionary as what Newton figured out is how he figured it out. He basically laid out a new rule for doing science. Don't make things more complicated than they need to be. Find the simplest, truest explanation that actually fits the facts. That idea, it's still at the very heart of science today.
The impact of the Principia was, well, it was astronomical. Its shockwaves are still bouncing around today. Because it wasn't just about physics. It completely changed how we, as a species, see ourselves and our place in the cosmos.
I mean, think about the big takeaways here. It brought heaven and earth together under one rulebook. It laid the foundation for physics for the next 200 years, and, maybe most importantly, it showed that the universe wasn't chaotic or random. It was a rational, predictable place that we could actually figure out.
Now, of course, the story doesn't end there. Science is always moving. For centuries, Newton's clockwork universe was the law of the land. Then Einstein came along and completely blew our minds by redefining gravity as curves in space-time. And now, quantum mechanics tells us the universe is, at its deepest level, kind of fuzzy and unpredictable. But here's the kicker. None of those later revolutions could have happened without the solid ground Newton gave us to stand on.
Which kind of leaves us with this big, lingering question. Newton handed us this beautiful, predictable, mechanical universe, like a perfect clock. But the deeper we look, both into the vastness of space and the tiniest bits of matter, the weirder and less certain it all seems to get. So, I'll leave you with this. Are we still living in Newton's universe?